Hello, everyone. Today we're going to be talking about slope fields. This is the last topic of new material that we are going to discuss for this year. And then after this, we will really start reviewing all kinds of different topics that we talked about throughout the year until you guys take the AP test. All right, so slope fields. It's just a pictorial representation of all of the possible solutions to a given differential equation, which we just talked about late last week. So, just remember that a differential equation is the first derivative of a function. Thus, the solution to a differential equation is the function f of x or y. So if I look at the differential equation, dy over dx is equal to x plus 3, there's an infinite number of solutions for that, because I know if I find the solution to that, I'm going to end up with a kind of a plus c. So that's going to be the general solution, and it kind of represents just all of the possible quadratic equations then this could actually could be to get dy dx to be x plus 3. So there are 4 things that you really will have to know how to do for the AP test. Number 1, and we're going to look at some examples of each one of these, and I'll kind of talk briefly about each one of them. But the four are, number 1, sketch a slope field given a differential equation, dy dx. By far the easiest of the 4. Number 2, given a slope field, draw a particular solution. Also not bad. Number 3, match a slope field to a given differential equation. A little bit more difficult. And then last thing, match a slope field to a solution of a differential. Also not bad. Really, I think slope fields are not entirely too difficult. They look weird. But really not too bad. All right, so number 1, sketch a slope field for a given differential equation. So just keep in mind, a slope field should look like a collection of f of x's, not a collection of f prime of x's. So it should kind of look like your function. If I look at this slope field over here, and if I were to draw maybe a solution to a specific value, it might look something like this. It's basically, in this case, because of my differential equation is x minus 1, I know that when I find the antiderivative of that, this is linear, so my solution is going to be quadratic. My slope field should look like a collection of a bunch of different quadratic equations. And then the hash marks are basically just the slopes of your tangent lines of all of these different places. So to get this slope field, what you would basically need to do is anywhere that they have a tick mark on the graph, you're just plugging and chugging values into this differential equation. And then you're drawing a little tiny line that has the slope of that answer. For example, negative 2, 3. If I plug in negative 2, because I can't really plug in 3 into my y value because I don't have a y value. So if I plug in negative 2 minus 1 is negative 3. So if I go to that point, negative 2, negative 3, I'm drawing a little line that looks like it has the slope of about negative 3. So then I just repeat that, and I do it over and over and over and over again until my entire chart's filled. If I look at all of these x values of 1, the slopes of all of those, what's 1 minus 1? It's 0. So I know when I plug those in, all of those slopes would have to be a horizontal tangent. And then I would be done once I plug them all in. So there's that example. That one was pretty easy. Didn't really have a y value that was involved. If I go down here to the next problem, So now my differential equation is x minus y. So now I'm just plugging in all of my ordered pairs that are in this chart for x and y and then drawing what my slope would be. The easiest in this case would be where x and y are the same value, because if I subtract the same thing from each other, I'm going to get equal 0. That's why at 0, 0, we have a horizontal tangent. 1, 1, horizontal tangent. 2, 2, horizontal tangent. And then from there, I'm just basically drawing all of my other graph or plugging in all of my other points. Plugging in all of my other points into my differential equation and just drawing graphs. I mean, that's simple. Number 2, given a slope field, sketch a solution curve through a given point. So this first one, kind of going back to this previous problem that we had on the last page, dy over dx is equal to x minus 1. It says sketch a solution curve through the point 1, negative 1. So step 1, go to 1, negative 1 and make a dot. There it is. All right. So I know that my differential equation is linear. So my solution should look like a parabola, because that's 1 degree higher than a linear function is a quadratic. So I'm just going to draw a quadratic equation, kind of matching up with all of the lines that are drawn. And I have to make sure I go through the point 1, negative 1. That's most important right there. So I better have that point on our graph that we're drawing. And there it is. Next example. Number 3, match a slope field to a differential equation. Okay, so since the slope field represents all of the particular solutions to a differential equation, and the solution represents the antiderivative of a differential equation, then the slope field should take the shape of the antiderivative of dy dx. Match the slope fields to the differential equations on the next page. So if I go down here to the next page, number 1, our differential equation dy dx is sine of x. So I need to think, all right, what is the antiderivative of sine of x? It's negative cosine of x, and then plus c. So I need to go look at my graphs and which of these graphs looks like cosine. Okay, cosine's periodic, just kind of goes up and down, up and down, up and down. And the one that looks like cosine, we really have 2 that I think you could probably choose from, which would be I and D, just because it looks kind of like periodic cosine shape. And you just have to think about it like, all right, I, at 0, 0, what's the value of cosine of 0? Let me think here. That's the 0, and then I look, and there it is. Well, I can't point with my finger. You can't see. So, right there, if I zoomed in, we'd be able to tell what the slope is right here. And then we can go from there and choose that one. Now, if I look at number 2, that's linear. My differential equation is linear. So I know when I take the antiderivative, I'm going to have a quadratic. So I'd go back up here and I would look and be like, all right, which one of these looks like the graphs, like a bunch of graphs of quadratic equations? I would have A and really F probably. So I would say between those 2. Let's go find where F is. There it is. It says x squared over 2. That one right there, it would definitely be horizontal tangent at 0, which it does. And I think about, negative b over 2a tells us our or where our max or min would be located. In this case, it would be 0 for that one. But for all of these, you're basically looking at the differential equations, thinking about, all right, if I took the antiderivative, I get my function, which one of those graphs looks like a collection of that type of graph? If I look at number 3, the antiderivative of e to the x is e to the x. So which one of those looks like that? It's b. All right, and then the last thing that you have to do is match a slope field to a solution of a differential equation. So when given a slope field and a solution to the differential equation, then the slope field should look like the solution, or y. So in this case, we have my original function. All of these are y equal. So these are the solutions, the general solutions. So I'm just going back and be like, all right, well, number one is y equals x. So which one of those graphs looks like a bunch of straight lines? And there it is, C. C looks like a bunch of different straight lines and then basically just moving it up or down. Number two, y equals x squared. Which one of those graphs looks like a bunch of quadratic equations? A. And then we can go from there. So this one's a little bit different than the last one because on the last one, it gives you the differential equation and you have to think about what the antiderivative would be. Then you're comparing your potential antiderivative to the graphs. These, not so much. You already have your antiderivative and you're just basically looking at your equation and then comparing the graph and trying to figure out which ones match up the best. So we got two questions down here. The first one shown below is a slope field for which of the following differential equations. So one of the nice things about like this problem is I can just, since I have all of my answers of this multiple choice question are differential equations, and I really can just pick a value, a test point, and plug it in to see if I actually get what I think. So with these, all of these points right here, when x is equal to -1, all of the slopes at those places would be 0. So they just chose -1 and 1. So I'm just thinking if I plugged in -1 for x and plugged in 1 for y, I need it to equal 0 because that's the slope at -1, 1. So if I plugged it into A, -1 times 1 is not 0. If I plugged it into B, -1 times 1 minus 1 is not 0. It works for C. It does not work for D. And then E, if I plug it in, it does get 0. So I need at this point to pick a new point. Pick a new point and plug it in. So now I'm down to C and E. So I know, let's see, they just chose -2, -1. So -2, -1 has a positive slope. So if I plug in -2 and -1, I need my answer to be positive. So if I chose this one, -2 times -1 plus -1, that is positive. This one, -2 plus 1 is -1, -1 cubed is negative. So that one does not work, hence why your answer is C. This last one here, consider the differential equation. dy over dx is equal to x over y. A, on the axis below, sketch a slope field. So to do this, all you are doing is just plugging in all of these values, 1, 0, 2, 0, 1, 1, 2, 1, all of those ordered pairs that are on that graph, you're plugging it in for x over y, and then just drawing a little tiny line that looks like the slope of your answer. B, sketch a solution curve that passes through the point 0, -1. They've done that. That's just a rough sketch. It doesn't have to be perfect. And then C, find the particular solution to y equals f of x to the differential equation with f of 0 equaling -1. So this kind of goes back to solving a differential equation. So I need separation of variables. So I'm going to cross multiply. I have y dy is equal to x dx. I would integrate both sides. Y squared over 2 is equal to x squared over 2 plus c. Now I am plugging in my value 0 for x, -1 for y. So that way I can solve for c. I get c is equal to 1/2. And at this point, now I need to go back. And solve this for y. So I'd multiply both sides by 2. Y squared is equal to x squared plus 1. Take the square root and then try to figure out, does that need to be the negative or positive root? And remember, when we are deciding that, we're taking that ordered pair and plugging it in. And if I plugged in 0, 0 squared plus 1 is 1. The square root of 1 is 1. It needs to be -1. So is it the positive or negative root? It needs to be the negative root. All right. So that's the end of the notes. Do day 60 homework and get that to me by Wednesday morning. On Wednesday, I'm going to start posting some videos and stuff to do for reviewing. Hope you guys are doing well, and I'll talk to you soon.